Good morning. So far, we have seen how to design a Turing machine and the techniques for construction of Turing machine. Today, we'll see variants of Turing machines. So far, we have seen a single tape Turing machine. So, single tape Turing machine, which was made up of cells, and you had a read and write head, correct, and a finite control. This is what we have seen so far. And we also saw the movements like you could move the transitions were like this, isn't it? That is delta q on a. You are in some state on getting a symbol a, right? You would make you may make a transition to state q and change that symbol a into something called as a y, and then direction. So direction is like right or left or stationary, which means not defined. So now we'll see two new models of Turing machines. One is where you have more than one tape. This what we saw was a single tape so far. So if you have more than one tape, then we call it as a multi-tape Turing machine. And also for this delta q comma a, here there was only one option. Instead of that, if you have multiple options, so that means it is non-deterministic, isn't it? For same state and same symbol, if you make more than one move, then it is non-deterministic. So that's called as a non-deterministic Turing machine. So let us explore one by one. So let us first take a multi-tape Turing machine. You can see an example here. You have multiple read and write heads here, and you have more than one tape over here. So, excuse me. Obviously, a multi-tape Turing machine will have some states. So, finite set of states, and it will have an initial state like Q naught, and a subset F is final states, right? And we'll have, let us say, a set of P tape symbols, some number of tape symbols which we denote using tau, and a new symbol B which is not in P. This is called as a blank symbol. Okay. So these are all. So blank definitely will not belong to our alphabet set, right? And this tau, whatever the sigma is always a subset of tau. All right. So this same definition, what we know already. Only thing is now we have three tape. Here in this example we have shown three tapes. But if I put a dot dot here, any number of tapes, multiple tapes. So let us say we have k tapes. Okay. Let's call this as tape one, tape two, etc. And let us call this as a tape k. As you can see, each tape is divided into cells, right? First tape always holds the input string, that is W, when we begin with. Second and any other number of tapes will initially contain the blank symbols. Okay, they'll all hold the blank symbols. So head of the first tape, we call it as an input tape because it has an input string. So we can call this as input tape. So this read and write head of the input tape in the beginning, okay. So it will point to the left end of the input. So if the input begins here, for example, input could be CAC, something like that. So it will point to the left side, that is left side of the input. The same thing we have seen till now, isn't it? Whenever you wanted to do a configuration, initial state, and then you have all the symbols. So here also same. So it will be at the left end of the input W. Left end of the input W is this one, correct? Left end of the input W means first symbol of the input is this. Okay, and we can also declare or define delta. What is delta? Delta is partial transition function, right? So this transition function, I can say that it will map into this. So what is the meaning of this? It's the same definition which we have used for all other things also. Only thing is you can see a K here, means for each tape. Multiple tapes come into picture, right? So since multiple tapes come into pictures, I have written the translation as to the power K. Means when K is 2, second tape, K is 4, fourth tape, like that. Alright. So how many heads are there, read write heads? If you have K tapes, obviously you will have K read and write heads. So what are the typical moves in a multi-tape Turing machine? What are the typical moves? Obviously, one of the moves is changing the states. So M enters into some new state, right? This is one move. Second one is you will write new symbols in cells, right? You replace some symbol by some other symbol, or you write new symbols. Okay, under the you will write symbols in the head, in the cells which is pointed to by the head. Then the third one is each tape head, each tape head moves either to left or right or remains stationary. One thing you should remember is that heads will move independently, means this can be moving to right, this can be moving to left, so they move independently. Okay, or some may not even move. That's why we have stationary. So the initial ID has the initial state as Q naught and the input is W, right, in the first state. And remaining K minus 1 tapes will have blank in them. So what is an accepting ID? This is initial ID, what I said. So accepting ID will have final state, right? Will have final state, and it will also have some strings in each one of these tapes, right? So initial ID is, means when we begin, this is W, this is blank, and all others are blank. So what is final ID? Final ID is acceptance state, correct? So when you have final ID or accepting ID, we say it has a final state. And what else is there? So as you know, we have written move left, right, etc. So in remaining K minus 1 tapes, we'll have some strings. This is our multi-tape Turing machine. There are one or two theorems. Usually it doesn't come, but anyway, since it's very easy, I'll tell you anyway. So the first theorem says every language accepted by multiple Turing machine or multi-tape Turing machine also should be accepted by a single Turing machine. Okay, means whatever example I showed up, it had multiple tapes, isn't it? So it says that there should be an equivalent way of converting this problem into a single tape Turing machine. So how we can do this? It's simple. We can actually simulate using the tracks. Means, see here one diagram I'm showing. You can imagine this like a single tape only, single tape Turing machine. But in that one tape, I divide this into multiple tracks. Okay, multiple tracks. Now, let us say if we have to simulate K-tape Turing machine, which we saw. Here what we'll need is, we'll need 2K tracks. Why 2K tracks is because currently where I am, to denote that, you remember here in diagram you are seeing two read and write head, but actually only one read and write head will be there. Okay, only one read and write head will be there because it is a single tape Turing machine. Alright, it's a single tape Turing machine. So since it's a single tape Turing machine, you have only one read and write head, but you are simulating multi-tape Turing machine. In multi-tape Turing machine, you have multiple read and write heads. So what will I do? It's simple. These two, if you see, okay, this X you see, no? X is like a read and write headed. We are using a marker to say A2 is under observation, or I have to do something with this A2. So similarly, these two tracks, if you see, now B5 is under investigation and you also have a marker called as X. So this X will simulate multiple read and write heads. Though we have only one read and write head in single tape, this X is showing us that X is simulating the multiple read and write heads. Okay. So I hope this is clear. So what is happening over here? So for K tape, we need 2K. One for actually storing the information and one is to store the marker, okay, which represents the respective tape head. Okay. So now the question was, can I accept, right? Whatever is accepted by multi-tape Turing machine should be accepted by the single tape Turing machine also. So how do we do? Let us take only two tracks here. We are simulating only two tracks. So tape 1 and tape 2 only. Alright. And this will be holding good to anything else also. How many ever tracks. Alright. So here M1 M1 means the machine will have to visit every head marker. Now, earlier, when you have multi-tape Turing machines, let us say this is one tape, this is one tape, this is one tape, the finite control had multiple heads, isn't it? So, on one transition function, this was doing something, this was also doing something, and this was also doing at the same time. Now, I can't do it at the same time because I have only one head. So, what I have to do? I have to go to first marker and make whatever changes I have to do here. Replace it, move left, right, whatever, stationary. After that, I have to go in search of the second marker and again make changes to this B5. So, if you have multiple such things, I have to do it for everything. Okay. So, since we do this is a simulation of single move, isn't it? So, at the end of one move, we are just going to the next move based on the revised positions and based on the current head markers wherever they are present. So, obviously, M1 accepts the string W if the new state that is recorded now, right, is the final state. It's simple. So I did here, I did some action. After making the action, I have to change the state or whatever that is there in the finite control. So when I complete all the actions, if I have reached the final state, then it will be accepted. So one of them will be definitely accepted. Okay. So this is one here. The next one is, if M1 is a single tape Turing machine, okay, if M1 is a single tape Turing machine, which is simulating the multi-tape Turing machine, then the time taken for simulation of n moves is O of n square. Okay, that means I require n into n time to simulate. I hope the question is clear. I'll repeat it. See, it's saying that if I have to do n moves for this multi-tape Turing machine, when I simulate it using a single tape Turing machine, it will take me O of n square moves to achieve the same thing I would do using one multi-tape Turing machines. I hope this is clear, right? So how can we justify this? You can see here, let M be a K-tape Turing machine, okay, and we are talking about n moves, right? So after the n moves of that machine, the head marker of M1 will be separated by 2n cells or less, correct? I hope this is clear. So you have n moves made, right? We have simulated it like this, isn't it? Just see here, we have simulated it like this, okay? And you have to make n moves, right? So suppose, let me just rub this off to give you a clear vision. What is the maximum move I have to do? Let us say this is my first position, okay? And n moves, right? So this much is n moves. Let us say this X marker is in the first position here for this combination, for this stack. And let us assume that this X is at the last track. So if this is n moves, if this is n moves, so what is the maximum distance between these? 2n moves, correct, no? You have 2n cells difference between the two heads. So that's what we are saying here. So after n moves, because each one can move left, right independently or remain stationary. So after the n moves, the head markers will be separated at the maximum by 2n cells. They can be less also, right? They can be less also. Alright. So we call this as a gap. 2n cells is a gap. So to simulate a move on M, the Turing machine M1 has to visit all k head markers, isn't it? Again, I'll repeat what I'm trying to say here. To simulate one movement here, you had three heads. So you just made one move, either to the right or to the left or to the whatever. But here to make these three moves, I have to visit three head markers which are very far from, which could be far from each other. So that's what he is saying here. Okay. So to simulate change in each tape, you may have to check by moving left by 2n cells, right? So means what? At most two moves in reverse direction in each tape you have to do. So M starts with the leftmost head marker and you have to go through all the head markers, right? And to go through all the head markers, the maximum gap is 2n. So at the maximum, for each head marker, you are going to make 2n cells, right? So you may have to move left by 2n cells in those tapes. Go ahead and again to come back to the original direction, again extra two moves, correct? So total number of moves by M1 for simulating one move will be 4n plus 2k. I hope this is clear. Why 4n? 4n because 2n move to locate head marker, right? 2n move to locate head marker and 2n plus 2k move, right, for simulating change. So when you add them, it becomes 4n plus 2k. So since it is 4n plus 2k, n into 4n plus 2k, you've studied this in data structure or in ADA, right? So this becomes 4n square. So since it's 4n square, the time required is O of n square. O of n square. So I hope this is clear. So we were talking about two variants. The first variant is multi-tape Turing machine. The next variant is non-deterministic Turing machine. So everything else remains same. The definition of Q, tau, B, sigma, Q naught, F, all of these are same. So what is different here is this delta now is a partial function. Partial function means you can see usually what do we say? It maps Q into tau into Q into tau into L comma R. But now you are saying into a power set of Q into tau into left or right direction, which means you will have multiple possibilities for movement. From beginning, even from the NDFSM, you know that is the definition, isn't it? So what I am trying to tell here is when you are in some state Q and on seeing a symbol A, usually for a Turing machine, you go to some state called as P, you might replace A by Y and you will either move right or left or whatever. But now instead of having one such transition, I might have multiple transitions. I may remain in queue itself and not replace anything, just move left also could be there. Or I may go to a state called as R and I can replace this A as blank, and I may go to the right, and like this you may have multiple options. So that's why it is called as a non-deterministic Turing machine. Okay. Now regarding the non-deterministic Turing machine, you have a few theorems in the textbook. So one important theorem over there is, if M is non-deterministic Turing machine, then there is definitely a deterministic Turing machine M1, means equivalence. For every non-deterministic Turing machine, there is an equivalent deterministic Turing machine. That's what we are trying to say. Now here, we can construct M1. Alright. So what is M1? M1 is, remember, M1 is deterministic Turing machine. M is non-deterministic Turing machine. M1 is deterministic Turing machine. Okay. So the proof is, we'll construct M1 as multi-tape Turing machine. Okay. It's easy to do that. So let us construct M1 as a multi-tape Turing machine. You can see the diagram on the left hand side. Alright. Now what we do is, each symbol in the input string, we know, may lead to a change in the ID, isn't it? This is what I said. Every symbol in the input, right, might lead to a change in ID. So it can lead to this ID or this ID or this ID or any other ID. So M1 should be able to reach all IDs and stop when an ID containing final state is reached. Is this clear what I said? So each symbol, I'm talking about this, each symbol, right, leads to, in input of course, leads to new configuration, right? Leads to new configuration, or you can say change in ID. I'll call it as change in ID because it's represented as IDs over here. Okay. Now, M1 that we are designing, right, should be, stop when, because it is deterministic, it should stop when some ID, which contains final state, obviously, should be reached. Okay, I hope this is clear for you. Now, how do we actually do this? You see here, we are making use of two tapes. All right. And the first tape is there, no? In that first tape, we are storing the IDs of M. All right. And also the state of M. So you have multiple IDs here, ID1, ID2, ID3, ID4, ID5, ID6. And this is a star. We are using an extra symbol star, which will separate these IDs. So we can definitely store it in tau. That is, it is included as a tape symbol. Now, which ID I am currently checking? And that you can see there is an X over here, right? So this X is a marker, okay? So we can use this marker X along with the ID separator. I hope this is clear, okay? So what is the process? How do we process the ID? For example, now ID4, on the top of that you have X. So how do I process the ID? So the machine M1 will examine the state and scan symbol of the current ID. This will have multiple symbols, right? This ID4 will have multiple symbols. So what you do is you examine currently you are in which state, for example this, right? And what is the scan symbol? Something like this. Now using the knowledge of the moves that we have stored in the finite control, M1 will check whether this state is an accepting state. If it is an accepting state, then M1 will accept it and stop simulating the M. Okay, stop simulating the M. Suppose, let us say Q is the current ID. I'm just taking one example. Let us say Q is the current ID. Here, instead of taking one letter, right? Let us take X, Q, A, Y, something like that. Okay. So, if the state Q in the current ID I have taken is this. X, Q, A, Y. So, this is the current state Q. Let us say this is not accepting state. Okay. And let us also say delta of Q comma A has k triplets. I'll repeat again. What I am saying here is this is the ID. Okay. And you can see that this is state Q and the next symbol is A. So that means next I have to see what is the transition for Q on A. And let us say it has k triplets. Means here I have written 1, 2, 3 dot. Let us assume that it has k triplets. In which case what will be done? Okay. If it has k triplets, if it has k triplets, so M1 is there, no? The machine. So it will make copies of this ID. Okay. It will make copies of the ID at the end of the sequence. So this is ID4. XQAY is ID4 and Q on A has, so let us say some triplets, 3 or 4 triplets. So if this Q is not final state, suppose it's not final state, you can see you have ID6, no? After that, if nothing else is there, now I am going to create multiple IDs. So basically k more IDs based on delta Q on A where all it will go, right? Delta Q on A where all it will go. For example, A might be changed as B and this Q might move to right side and it may become P1 and something else like this. So M1 modifies these k IDs in tape 2, okay? According to the k choices that we have for this. Okay. So where does it make the changes? In tape 2. So M1 finally returns to the marked current ID, this one, erases this X because we are done with this X, right? And it marks the next ID separator star with X to continue with checking for that, and this will continue till we have done with everything else. Okay, so today what did we see? We started the class with variants of Turing machine. We have two variants of Turing machines that we are talking today. One is multi-tape Turing machine and the second one is non-deterministic Turing machine. So in multi-tape Turing machine, after telling what it is, we saw one example here where we start with W being in the first tape and remaining being blank, and these being the moves, typical moves. And then we also talked about how a language accepted by multi-tape Turing machine is also accepted by some single tape Turing machines. So for this, we have simulated the multi-tape Turing machine by single tape Turing machine, which has multiple tracks. and two tracks are used for one ID, that is one for storing symbol, and the second one is to store a marker which represents the read and write head of multi-tape Turing machine. Then we talked about the moves, right? If M1 is a single tape, then simulating the multi-tape Turing machine, then time taken for this M1 single tape to simulate multi-tape will be O of n squares if we have n moves. So this is based on the gap that is separated between the two markers, and we saw the proof for that. And finally, we talked about what do we mean by a non-deterministic Turing machine. So in non-deterministic Turing machine, how we can convert it into a deterministic Turing machine by taking the help of multi-tape Turing machines. Okay. And with this, I'll stop today's class. We have one more topic, linear bounded automation, which will complete our fourth module. Okay.